Welcome again for the second and the last talk for the day and also for the seminar series this year. Uh, Today we have Professor Yanzhi Zhang, who is a Gray Havner Endowed Professor in the Department of Mathematics and Statistics at Missouri University of Science and Technology. She received her PhD in computational mathematics from the National University of Singapore in 2006, completed a postdoctoral appointment in the Department of Scientific Computing at Florida State University, and joined the faculty of Missouri State SNT in 2010. Dr. Zhang is current research interests include data-informed modeling for seismic waves, reduced order modeling, fractional and non-local PDEs, and multi-scale multiphysics modeling and simulations. We are very happy to have you here. You may please begin your talk.
Thank you. First, I would like to thank Pavan and Arran for this for the kind invitation, and also like the contributions to the community. So today, my talk is based on our recent work on this heterogeneous medias for the anomalous diffusion in heterogeneous media. So it is similar or like in some sense similar to the I think it's Professor Fedotov's talks on October 31st. Oh, sorry. Yes. So today, at the beginning, I will give a brief introduction, although the Professor Chen has already gave a nice the introduction about the like heavy tails. But I will give a brief introduction about the fractional Laplacian, and then what's the motivation and the challenges when you're trying to solve it numerically. And then I will discuss two of our recent methods, like the Fourier spectral type of methods or the meshfree methods, and followed by some numerical experiments and applications. So, this is the fractional community. I assume everybody is already very familiar with this constant order fractional Laplacian. So usually we refer it as a generator of a symmetric alpha stable Levy process. So there are many different definitions, but there are two well used definition, especially for the numerical methods developer. Is one is a pseudo differential representation, so it's based on a Fourier transform. So here it is like the alpha is allowed to be any real values, it's like positive values. And the other one is based on the hypersingular integral. So here C is a normalization constant, and PV stands for the principal value. And so in this definition, so you have the strong singularities, like when y approach x, and here alpha is allowed only between 0 and 2. And if you want to see more like the definitions, so there's like a nice paper. They talk about 10 different equivalent definitions for this operator. So it's like in a previous talk, we already see there's many different applications of the heavy tail type of dynamics. So for the Levy flight, so far they have already found in many different applications, like in physics, in biology. So for example, this picture, here, I got it from the reference number 3. So it's talking about the observation of the bacteria. If you check the individual bacteria, actually you find out their trajectory is not a Brownian motion. It's more like the Levy work. So also these days Levy flight has been used in a study the fluid dynamics, or the study the seismics. So today is we are mainly interested in a variable order type of the fraction Laplacian. So compared to the constant order fraction Laplacian, so the variable order, it is more like the stable a fellow process. So in terms of definition, so far I found like in this review paper in Samco's, they have generalized the constant order to the fractional Laplacian order by changing the power alpha constant to the spatial dependent. Of course, here like the alpha could be like the time dependent, it depends on some of the application. But here we will mainly focus on the spatial dependent. And also like the hypersingular integral form, we can also generalize to the to the function spatial variable function. And here the c is also become a function instead of constant. So like this type of the why we interested in this type of the operator, and it is like the recently like for example this heterogeneous type of medias has been found in many different applications. So for example, this is one from this reference. They talk about this genome dynamics, and then they find to do the fitting. They find so for example use the diffusion equation to fit the experiment data. They find the this diffusion constant, it is variable, and also like the powers, actually, it is also spatial dependent. And so this different color represent the different powers, like that fractional, you can thinking about that fractional alpha powers. And also like the one of the director like the motivation is like the with our collaborators they in physics in geophysics they have already using like the variable order fraction Laplacian to study like the seismic waves propagate under the like the ground. So for example, there's a earthquake happens, and then like the seismic waves gonna go through like different medias under the ground, like the rock and the sand and the fluid. And a different material has different quality effect. And actually, that is like the Q here. It is related to our power alpha. So it will affect the dispersion and the attenuation of the like the waves for different media. So for that reasons, like so here we are interested in variable order and fractional Laplacian. And now you so in the last 10 years, so for the constant order fraction Laplacian, there has been a lot of the numerical studies for the like the constant order, including like the our group. We have developed the spectral type of methods and the finite difference methods and the mesh-free methods. And there's also like a lot of the five element methods by other groups. And recently, there are like the two kind of review papers about the fractional diffusion or like the nonlocal fractional models. But these are all focused on constant order fractional Laplacian. And compared to the constant order, so the like development, especially like the numerical method development for the variable order fractional Laplacian is still very behind. And so recently in our group, we have also developed these two methods and also like a finite difference method. And in a while, my talk will go through like both methods a little bit. And of course, like in a field, there's because like the challenge, significant challenge for the variable order. So some works also developed to either the truncate the variable order fractional Laplacian to make it easy to discretize, or they introduce different definitions slightly like the to have a easy development of the methods. So now let's see. Okay, so move from constant order to the variable order. So what are the new challenges come from? Why like so far, as I mentioned, in the last 10 years, there has been a lot of numerical methods developed for the constant order. So why not we cannot use them or bother them to work for the variable order? So here, so let's focus on this hypersingular, the definition. The reason is many methods was developed based on this definition. The reason is it's easy for incorporate different boundary conditions compared to the Fourier kind of pseudo differential definition. So this operator come from the constant kind of can consider as a generalization of the constant order. Of course, it will inherit all the challenges from constant order. It's non-local, and no matter what is your physics domain you're considering. So the interaction domain here you consider is entire domain. So that's like the second, has a strong singularity. So the when the y approach x, you have to be very careful about when you design when you discretize your scheme. And so the new challenge here, it is of course, it's introduced by this spatial dependent alpha. So then because of this alpha become a function, so this makes almost all the numerical methods available for the constant order, not work for the variable order case. And so for example, one of the direct impact is for the constant order, when we discretize it with a finite difference of y element method, after you discretize it, then we find out the matrix actually can be the symmetric toplets matrix. So in other words, it allows a faster numerical algorithm with low memory and computational cost. However, because now you have alpha, it depends on the space, then this property is gone. And you have to save the entire matrix. So thinking about if you are solving the 2D, and then you need to save the entire matrix, and that's itself, it's memory cost, it is almost impossible, no matter, not to mention even to do the matrix vector multiplication. So as I mentioned, this variable order has been used in literature of the geoscience, geophysics. So how they handle this case? So in their literature, to reduce or to get rid of these challenges from this spatial dependent alpha, what they do is they in a certain region, local or the global region, they integrate this alpha out to consider as a constant or averaged alpha. So in this, by doing so, then they can reduce their variable order fraction Laplacian to a constant order with this averaged power. But then it makes the computation much easier, but the consequences, you are not describe the heterogeneous media anymore. You become a homogeneous. So the many of the properties you cannot observe. So these are the main challenges of the variable order. So given these challenges, so there's so far the method development in this field is still quite behind compared to the constant order case. So today I will discuss the two recent our development, and so also I will use this to show the more details the challenges caused by this variable order. So now let's first consider this Fourier spectral method. So this is the easiest one. So for example, I will use this a one-dimensional waves. Our methods can handle the multi-dimensional, but let's just use this one-dimensional linear waves to as an example. So this is so let's consider as the problem on the torus and with a periodical boundary condition. And classically, when you're trying to design a Fourier spectral methods, so you assume a solution ansatz. So you can solution can be written in a Fourier series way. And so then by this definition, sorry. If we directly use the definitions from the Fourier pseudo spectrum definition, then we immediately can get this approximations of this fractional Laplacian written in this form. So here, like we're gonna have the symbol. It is like this frequency to the power alpha x. Well, you will see like currently this is straightforward compared to the constant order. So what's the challenge? The challenge is how you're gonna compute this one. So it is like for like you can approximate in this way, but how are we gonna approximate it? How are we gonna implement it? So if alpha is a constant case, and then like what we can do is like we multiply this multiplier to the solution, and then this summation, we don't need to do the summation like one by one. What we can, this is equivalent to do the inverse FFT. So in other words, this summation can be easily handled with like the more efficient inverse FFT with computational cost of n log n. However, like so then like if you have like the time dependent problem, so if you substitute that form here and then take the inverse Fourier transform at both sides, then we can get like the simply for the constant case, then we get like this decoupled system in frequency space. So in other words, the space has been already well resolved by the FFT, and then like now we only need to do the only need to handle the time, and as soon as we find out the time and find solve out this u hat, and then we do the inverse Fourier transform back, and then we get the u. So this is like for the constant order case, so it can be efficiently handled. However, like if you have like the variable order case, so the this part cannot, this summation cannot be efficiently calculated by the FFT. Actually, you cannot use the inverse FFT. So that means like the only way to handle this summation is you can only straightforwardly really like sum it out. So the computational cost is increased like dramatically. And if you handle like the time-dependent problems, so if you apply the like a Fourier transform at both sides of that equation, then this is like the at most we can push to. So there's no decoupled system. So in then we get like in a frequency space, we end up like the fully coupled like the ODE system. So this is kind of like how this small like the change of the variable order significantly change of the some well-known approximations like for the problems. So in our case, like in order, in our case, like well, we still wanted to get like we still can wanted to get like approximate this like cheaply. So we have like in other words, if we directly approximate, still we write it into the differentiation matrix forms. So then we realize this matrix again. You can see this is involve the X, and then this is gonna be a full matrix. It's like the dense matrix, and then there's no any special structure we can utilize when we're trying to do the like the efficient matrix vector multiplication. So like so this is a kind of, hopefully I give you a kind of ideas what is this like the challenges like it's influence not only like the spatial discretization, and also it's related to or affect some of the well used time discretizations because of this consequence come from this challenge of alpha spatial dependent alpha x. So the matrix assembling become like more costly. For example, if it's a constant order, so it is a symmetric toplet structure. That means we only need to assemble like one line, one row or one column of the matrix, and so the computational cost is significantly low, and plus I only need to save the one row or one column, and so the storage cost is low. And so if it's a toplet structure, and then I can use like the fast Fourier transform to accelerate the calculation of matrix vector multiplication. But now if you have like alpha become a spatial dependent, so those like the properties are all gone. So you have to assemble the entire matrix. So the cost of storage is from n increase to the n square. And then the matrix vector multiplications, it's also going to be increased to the n squares. So that's like so that's the main like the challenge. So it makes matrix vector representations for this operate. It is although looks straightforward, it is not feasible in a practical implementation. So what we did like in our method is like we noticed the challenge like come from like this frequency and like this cause is a frequency Fourier frequency and alpha is spatial. So this frequency space mixed like the multiplier. So like that is so then like the notice this, then we trying to separate this spatial and the frequent dependent in this multiplier. So the technique is simple like the Taylor expansion. So then we instead of having like the variable order power, we make it as like a variable order a variable like the coefficient. And of course, like the here, like then the a symbol gonna be changed from the power to the log type functions. And then after we do that, then we substitute back to our fraction Laplacian. Then we get like all these powers like the all these like the operator. So here it is we still have our non-local operate, but this non-local operate it is has like the symbol. It is like has a constant order. It's not like depends on the space anymore, and the variable goes to the like the coefficients. So in other words, this non-local operator it is not when m equal to 0, so this non-local operator reduced to the constant order fractional Laplacian. But when m is larger than 0, it is a non-local operator, but it's not a fractional Laplacian anymore. But we still, after we use this structure, we still can use the fast Fourier transform to approximate this part. And since the power, like the expansion, so it's a decay faster, so we can truncate it to a large m. So then every time, so this part we can calculate and then multiply the variable like the coefficient and then add them together to recover the fraction Laplacian in a variable order. So in this way, the computational cost reduced to the j log j, so times m, because each terms then we have a cost of j log j, and so we have m terms. So but this m is much smaller than j, my spatial dependent, my spatial number of spatial points. And so here, like, cause I just wanted to show, like, the illustration about, like, to see the effect of the heterogeneous. So here, like, consider, like, suppose we consider a Gaussian type of function. So if I apply, like, now I just consider this simple, like, the variable order. And so if you look at here, so if red line, it is like the constant order. So clearly, because my function is symmetric, so this Laplacian of this function is also symmetric. But if we consider the like this blue line, it is variable order fractional Laplacian. So you see the heterogeneous effect. It's like it is not symmetric anymore, and become spatially like the changing. And also the right hand side, it shows for the different component their contribution. So we mentioned in the previous slides, you're gonna truncate it to the m terms. So m equal to 1, and here I just show m equal to 1 to m equal to 4. So you can see when m increases, so the values of the that terms reduce. So that's indicate after long term, after a large MV, it's safe for us to truncate. It is the contributions of the terms getting smaller and smaller, but we cannot ignore that the contributions for those terms like when m is small, so they still contribute a lot this heterogeneous effect. And also this left side also show us it is not a good idea as they're used in some of the literature to average this variable order by a constant order, because you lose the heterogeneous effect of the problem. And so this is some of our accuracy. So for these nonlinear problems, so we also propose to use the second order split step method to solve it. And then for mesh size, reduce from 1 to 1/8, we can see our method can get the spectral accuracy, the decay, no matter you have a constant order or the variable order. So this is works very efficiently for the both constant and the spatial dependent alpha. And this is show the efficiency of our method. And so the left side, it shows, okay, so there we compare if I do the effect of the different m. So when we truncate, we find that this m truncation, how big these terms should be depends on my mesh size. So if my mesh size is small, I do need to include more terms to get the stabilize the errors. So this circle one, it is represented the errors without any truncation. So this star ones are the errors for different truncated m terms. So we can see once m is large enough, so they get the same error. So that's indicate the accuracy when I truncate m. And so the efficiency we can see, so the directly to do the matrix vector multiplication, so you are accurate, you are the computational cost or a computing time, it's increased exponentially, and with respect to the number of points in a space. And but our mesh-free method it is increased a log scale. So actually we proved it's mj log j. So that's why it is. So if this is just a 1D case, so you can imagine if it's a 2D case, so this cost will be significantly reduced based from our methods. And so this is the wave, the solitary waves, behave in the fractional media. So here it's the first two are in a constant order case, and this is a square root of the Laplacian case, and this is original the constant order Laplacian. So so you can see initially my wave is symmetric, and during the dynamics, the solution still evolve, but still keep its symmetric structure. However, if it's the variable order, so it become changed significantly. So although, for example, in this case, my S1 along the space, the average of S1 is equal to 1, but you can see the dynamics between these two are significantly different. So this is again like we conclude we cannot use the constant order to approximate the variable order, although the variation part is like not big. So this is like our free spectral method. Now, next, like the free spectral method works pretty well if you have a periodic boundary condition. But now, if my problem don't have periodic boundary condition, let's say if we have like the well used like the extended Dirichlet boundary condition case. So then the method don't work for that case. So for that purpose, we have this so-called the mesh-free method based on the radial basis function. So first, I will introduce like two quick like the property of the variable order Laplacian. So these are the building blocks for our methods development here. So similar as a constant order Laplacian, so it has a translation and the scaling properties of this variable order fraction Laplacian. And one of the main property we used here is if my function u can be written in this generalized hypergeometric function. So here a, b are like the vectors. And then the fractional Laplacian, no matter you have constant order or variable order, and the fractional Laplacian u can be also written in the same hypergeometric function. And of course, like if like you have constant order, this parameter will be still constant vector. Otherwise, it's become like the function vector. And so this is a very important properties like for our method below. So notice like this is like because like we know like a hypergeometric function can related to many like the elementary functions. So for example, like we can write the Gaussian function in a hypergeometric function f11. Like the confluent hypergeometric function. Then immediately by that lemma, we can write the Laplacian of the Gaussian in terms of the confluent hypergeometric function. Or like for example, the inverse multi-quadric function. And so here this beta, it is a positive constant. Then we can also rewrite this into like the Gauss hypergeometric functions. So why we are interested in like this type of function? So here is just I give two representative radial basis functions. There are different radial basis function, but in a field of the RBF methods, so these are the two well used or like representative methods. So again, like so this is just show us like a different like give me the same function and then just show the different impact of the alpha, similar as what we observed before. So so this alpha is spatial dependent alpha significantly changes the properties of the solutions. So here, like to introduce our method, so let's consider our problem is defined in a physics domain omega, which is open bounded domain, and then here we're gonna consider like we consider the Dirichlet boundary condition. And so that's mean like u is equal to some function g, and if alpha equal to 2, that's mean I'm considering standard Laplacian, like the integer order Laplacian. So in this case, my boundary condition is only imposed on like the boundary of my physical domain. Otherwise, if alpha is less than 2, then I'm considering extended the domain. It's everywhere outside of physical domain. So this is like so in other words, I write it here because our method can work for both standard and like variable order case. And the numerical method, we're going to develop it like a radial basis methods, and particularly like, for example, as we just saying, we can using like the Gaussian or like a multi-quadratic or like the inverse multi-quadratic functions as a basis function. So as a setup, let's say I consider like let's assume like I'm considering like my physical domain is like this disk. And then like first of all, the RBF method as a preparation, I need to sample the RBF centers and then the test points. So let's say these red circles dots are like my RBF center points. And different from like the other like the methods. So here our RBF method can we only require the center points or like test points inside of the domain and along the boundary. Although we have the boundary condition outside of the domain, but we do not need the points. That means the more points, the more computational cost. We only need the points inside and along the boundary. Then like as a standard RBF like as a method, then we assume our solution can be written in terms of like the RBF basis and times some coefficients. So here we use the like the Gaussian functions as the example, but other RBF methods also can work under our like the methods. So that's like the here epsilon like it is called the shape parameter of the RBF. It's a given parameter, and xi is the center of the RBFs, and the lambda is unknowns we're trying to look for. So if we find the lambda, then my solution u is already known. So like you imagine now I'm gonna work on impose the fractional Laplacian on this u. That means lambda is a constant, so immediately it's gonna work on this like the um, uh, fractional Laplacian gonna definitely immediately work on this basis function. So recall what we have llama, then we find out actually this is immediately give me like each base can be rated by this confluent hypergeometric function. So notice this. Then we can first, we're gonna rewrite our fractional Laplacian. So it's like integral domain. It is like the whole space RD. But now we're gonna split it into two parts. Like the integral first integrate over the physical domain, and then outside of the physical domain. And then like I substitute my ansatz into like each terms. So here like then we change it from u to the u hat. U hat is like my RBF ansatz. And then here it is the same thing because y is outside of my physical domain. So that means uy can be directly replaced by my boundary condition. So that's like the gy here. And then now I'm gonna just do simple like the plus and the minus one terms. And then the good thing is I can move these two terms and combine with here. Then my integral become like the RD. And then the left part like this will remaining like the here. And then use the definition of the fractional Laplacian again, then this part RD, it's become like this is just the fractional Laplacian of my u hat and the approximation of my the RBF approximation of my u, and this is like my boundary effect. And if alpha is equal to 2, and then this c is equal to 0, then this term is gone. So that means your boundary effect is like it is like the gone. Only this term survive only when alpha is less than 2. You have the non-local boundary condition. But this part compared to like the first part here, this part is much easy. The reason is X is inside of physical domain, Y is outside of like the physical domain. So that's mean like you do not have the singularity when I Y approach like they are not in a different like a domain. So this integral can be easily approximated by the traditional numerical quadrature rules. And this part, then we can analytically written in terms of like the hypergeometric functions. So then immediately we get this is like after I substitute that hypergeometric function, this is where we like the first term, and this is like the boundary effect. So for the hypergeometric function, we already have there's already a lot of numerical methods or like algorithm to efficiently calculate it here. So then we can directly apply this and then use that to calculate here. So then we bypass or avoid to discretize or handle that singularities when we're trying to do the discretization. Basically, we wrap up that singularity in this hypergeometric function. And so that can improve the efficiency and then the accuracy. So as I mentioned here, we just discussed about this Gaussian, but we can apply the similar ideas to other RBFs, and as long as we can find that like the hypergeometric function basis. And for the numerical analysis of our method, we have in our like the preprint like about the to prove the accuracy of our method is like a spectral order. Um, so here I will just use some of experiment to show the accuracy. So this is like the one of the benchmark problems to solve the Poisson problem, and it has like the homogeneous Dirichlet boundary condition outside of domain. And so in this case, the exact solution is like this power compact supported function. And so here we consider different like the alpha like spatial. So this is like the made up like functions. So we can see like here we compare like the alpha 1 to alpha 5 are the different like the variable order alpha as we just seen. And then we also compare with the constant order. So from left to right, my number of points increase. So if I say like the number of points, it's from like the 5 to 65, we can see no matter you have a variable order or constant order, actually my accuracy reduces very quickly. Only with 65 points, I can get like the accuracy is 10 to minus 7 or 10 to minus 8. So similar problems. So in, for example, for the constant order case in the literature, if you use the finite difference of an element with 65 points, so probably you only can at most get like 10 to minus 4 or 10 to minus 5, like the of accuracy. So you can see the efficient, like the method has like the good accuracy. And so now, next, like a few minutes, I will quickly show some of the applications, like the example. So one is like the in this is in soliton, like the move traveling in a different media. So it's like the trying to see show the non-locality and the heterogeneity of the solitons. So here we initially like you consider like the two like solitons and the initial condition and the initial velocity. And so for this is well used examples or well-known examples. So in the classical media, so that means constant, in standard Laplacian integer order. So this solitons has like this elastic collision. So this is top view. So the soliton one is here and another one here. Initially, they're gonna travel, and then when they collide here, then they're gonna separate and then travel like independently again. So this is elastic collision. So after collide, they can get their recover their original shape and continue. And the other one, like you can see, just simply like the fractional media, and then like the from 2 to 1.9, this dynamics significantly changed. Actually, immediately, even you point like 1.99, and it is like the dynamics is significantly different. So it's not elastic anymore. So once it's climbed, it's actually once it's travel, actually there's like the waves gonna propagate outside, and then once it's climbed, so you can see it's not like recovered anywhere close to the initial shape anymore. And so this is like in this case, this is like the combined media. So the left side it is like the fractional media, and the right hand side is classical media. So you can see has some kind of before it's climbed, so it is like the solid in classical media work like the classical case. It's and then the fractional case it's already like the change, but after they collide, so they affect each other. So even in classical media, so the waves is not exactly like the classical. Like the in a standard wave equation, it's different. And so this is like the kind of snapshot of the solution initially, and and then like different times. So clearly you can see this is small like the multi-scale structures like the coming out like over the time. So this is like solid in this heterogeneous media. And another example is like I think this is a study like this coexistence of normal and anomalous diffusion. So here this is like the situations like they consider the two different kind of media is like separated by the membrane, and then at different regions, particles are involved with different diffusion mechanics. So here I use a toy model. It's not exactly like here. We consider this channel, and initially I have like some chemical concentrated at the center of the channel, and then over the time, then we consider like the different part of the channel has different diffusion mechanics. So then we consider the diffusion properties. So here, like we compare the different cases. So the left, like the column, it is for the standard, like the diffusion Brownian motion, and everywhere. So you can see like so over the time, so it's symmetrically it's gonna propagate, and actually it's diffuse very fast because the boundary condition is zero. And then in a fractional case, it's diffuse still symmetric along this channel, but it's much slower. But if you have like the mixed part, that means left-hand side is classic, and then the right-hand side, it has like the fractional. Then we have like some kind of interface happens at the like the middle, like the transition areas. And then like the density distributions at the channels is unsymmetric, and it's very different compared to like the previous two cases. So and the last example is like it is I'm gonna quickly show this wave propagation. This is one of the models they used in that seismic wave papers. They use this fractional model. They claim compared to the traditional model, this fractional variable order fractional Laplacian can simultaneously capture the dispersion and attenuation of the seismic wave. So and here like it's we consider as a simple case. It's like it's a one like initially there is some kind of explosion, or like there's a source of the waves, and so like here like in the media like the upper and below they have two different. You can thinking about upper is rock, below it is like the sand, different two different media. So this is like the similar as what they find out experimentally. They find like this waves like propagate outside, so it has a dispersion effect. At the same time, so it is started to do have the attenuation. So you can see the colors. It's kind of reduced. It's kind of get weaker and weaker. So that's like the similarly is this example is we just want to show our method can effectively catch this like simulate this problem and catch these properties. I think that's all like our kind of results. Let me quickly like summarize. So as I mentioned, like our focus, like interesting here, it is like since there are already a lot of applications, or they find a lot of very like the heterogeneous diffusion situations in practice, and but the computational still quite behind for this operator. So our focus is trying to design a numerical method, trying to like for this operator. So far we have developed this Fourier spectral methods, and it is efficient and spectral accuracy for the if you have like the periodical type of boundary condition. And but if you have like other boundary conditions, then it can be easily coupled with mesh-free methods. So this mesh-free methods, it can be easily to do the mesh refinement or like work well with different domain geometry. And one of the most important thing is computational like implementation. It's almost the same for any dimension. It's just the choice of the RBF centers will be different. And one of the nice properties, both methods we developed here, it has compatible for classical, fractional, variable order, or constant order. So this is like one of the unique features of this in compared to finite difference or finite element methods. For example, for the finite difference or finite element method, we know the method for the classical Laplacian, integer order Laplacian, and then the fractional Laplacian are different. But here our method, it can be combined everything in a single scheme. So recently we also have like the finite difference method and then parallels the schemes. So, and if you have want to more details, you can find in our reference. Thank you.
Thank you very much for the nice talk. For questions, please raise your hand. I'll call out your name in the order they appear on my screen. Okay, I don't have see any raised hands, so maybe I'll ask one or two questions.
Sure.
So basically, for the pseudospectral technique, rather than evaluating two sums, what you're doing is projecting on the projecting back. You're going back to the real space, computing the product, and then you're projecting back to the Fourier space, and then you're doing all these computations. Is that correct?
Um, uh, like for the Fourier spectral method, actually, like the Fourier spectral method, one of the why it's used well in the practice, it is because of its you can use the FFT and the IFFT right quickly to do the reduce the cost and so here the reason this failed it is because of this power it's blended with like spatial and this like blended together. So here, what we are doing is like we're trying to separate them, like move this to the coefficient. But this part, we still wanted to use the inverse Fourier transform. So in some sense, you're right. It's like we have to go between like the physical space, X space, and then we use the Fourier transform, go to the C space, frequency space, and solve the problem and then project back.
Okay. What about aliasing? You haven't talked about aliasing. I was thinking about aliasing.
This is also like the for that part it is the same as like the constant order, so we still have like aliasing errors.
Okay, but have you figured out how to how to get rid of aliasing errors? I mean, in the classical community, uh, there is like couple of techniques that they use to tackle the aliasing errors. For instance, if you have a nonlinear term, I mean, there is two-third or 3-2 law, and there is filtering approaches or something. So, have you looked into it?
We haven't go to that deep yet. We recently just made this made this method works, and then we haven't carried out like the detailed the numerical analysis or like further improve the method yet.
Okay, so numerical analysis part is also you're still undertaking numerical analysis part as well.
That's right. Yeah. So this is a kind of more with the collaborator, they wanted to find something which they can compute first, then like the, so that's like the some
Mm.
part of this work. Yeah.
I see. I see. Fair enough. I see. Professor Chen has a question. Please go ahead.
Thank you. Very nice talk. Very
Thank you.
interesting. I have a very entry-level question. What is the difference between Fourier spectra versus Fourier pseudo spectra? Why we use the word pseudo?
I think that is like the um usually like the that's a very good question. So
If I
usually
may
like
jump in, if I may jump in.
yeah, go
So,
ahead.
Okay.
so, let's talk about the classical technique, no, not fractional. So the distinction that they make between spectral and pseudo spectral is basically how they evaluate the nonlinear term. So when they did the fully spectral method for the nonlinear term, you end up computing two sums. So a double sum is too much computation. So in one day that would be n square operation.
Mm,
So what they said is like, let me take the function u, project it back to the real space, compute u square, then I can u square is also a function, right? So you can project it back to the then you can project u square back to the Fourier space or polynomial space or some spectral space. By doing this, they saved a lot of computations going back and forth spectral space and real space. So from n square they became n log n, at least in one day. And if you're in 3D, then for furthermore downs in computations. So this was very important for people who are doing turbulence, because you are doing very large simulations. So you want to get out, you want to extract every little bit of juice there is to extract. So that's the so in summary, the only difference is how do you evaluate the nonlinear term. That's it.
Uh, yes or no? The question is true. Here, I see the space-time separation of the solution answers. You have a t term and x term separated. So I call this the space-time separation. Is this the reason we call it pseudo? Yes or no?
Um, I don't think that's reasons like for the pseudo part. I think like the separate of the space and time, it is like the what your basis is only resolved for the space, so that like the time has to be carried by the coefficient, because there's no like we use a Fourier basis, so they can only resolve the time. So if you write in this linear form, so the time automatically must be resolved here.
Okay. So the space-time separation is an assumption, right?
Yes, that's like it is kind of, yeah.
But in general, the solution in UX comma T is coupled space-time. So, yeah, okay. Yeah, gave me a very good clarification. I have a question. Another question is regarding you used the single epsilon for the shape parameter for the mesh-free, and is that a standard assumption? You have to use the single epsilon here?
Very sharp question. So, okay, so in how should I say? In a traditional like or in a field of the RBFs, when you solve the problem, so this epsilon, it is like they often use like the single constant like across all the bases. But of course, like all the methods, like especially RBF methods. So one of the issue or like it is these basis function are not orthogonal. So that's like so that's potentially when you form the linear system like then you may have like the ill conditional issue. So that's like the make people like also involved to including ourselves. Actually, we have also considered the variable order, like sorry, not variable order,
variable shape.
variable shape parameters. Or sometimes we inject some kind of randomness into the shape. And so that's like we call this as a passive learning. It is like we prescribe like or predefined as what's epsilon, no matter constant or variable. Like also like recently we are like doing like active ways we trying to learn or like fitting like the epsilons like and it's find out it does like the epsilon need to be like the different depends on like the distance between of your points. Epsilon should be related to the distance in order to get the better accuracy and stable performance.
Yeah, intuitively, because you have heterogeneous media, and it makes sense also talking about the shape is also heterogeneous.
That's right.
It's a
Yeah, it's
space
exactly true. Yeah.
dependent. Yeah, yeah.
Yeah.
Then there must be an optimal distribution of those shape parameters and anybody existing work and
No,
okay.
there's nobody. So I think like uh, uh, so I think go back to 2021 was the first work we trying to use this
uh,
RDF to the fractional case. So the reason
uh,
is like we were bothered too much by that singularity, like a kernel. When we discretize it, then it's
uh,
difficult to analyze, difficult to implement. So we're trying to find a ways to ignore or like bypass that singularity. So that's why
yeah.
we started to tackle this direction. Yeah.
Mm. So
But
I use the term is called a matched uh, a complexity matching. So the heterogeneous genearity matching could also this is a conjecture. Your epsilon x should also match to the heterogeneity itself.
that's
So
yeah, that's definitely I agree. Yeah. So actually, like we haven't matched the epsilon yet. We matching like when we sample the RBFs, so different places,
centers.
we do the different density of like center points.
Mm.
But it's just the epsilon term is too challenging. We haven't really make
Ah,
much progress on that direction yet.
okay, excellent. Thank you.
Thank you.
Mhm.
Are there any more questions or comments? You may unmute your mic. I guess no. So let me thank the speaker, Professor Zhang. Thank you very much for this nice talk. And with this, we close the session for this year. Thank you very much for all for participating.
Thank you. See you
Thank you.
26.
Already 2026 almost.